Hello, this is a presentation for leveraging temporal data for automatic labeling of static vehicles. The motivation for this research is based around the rapid development of object detection for autonomous vehicles. With the release of comprehensive driving datasets like KITTI comes the ability to train and test methods for 3D object detection. For the field to continue to grow, more data will need to be procured to capture changing environments and advancements in data collection technology. The issue with dataset formation, however, is that labeling objects, especially 3D objects, requires manual labor, which can be difficult and time-consuming. As such, we set out to find a method to assist in the procurement of 3D labels. Over the course of a drive sequence, a moving ego vehicle will perceive static objects differently throughout the drive and thus gain more information about its extents. Using this concept, we investigated the use of a pre-trained object detection network to generate predictions over the course of a drive sequence. When comparing different predictions of the same object, informed estimates are found to be more consistent, such as the width when the front or back is viewed, or the length when the side is viewed. By strategically combining these various predictions, a more accurate representation of the underlying object can be determined, and the final prediction for the object can be used to generate labels for that object throughout the sequence. The difficulty in combining detections for the same object comes with its own hurdles, as knowing which detections should be associated together requires the ability to track objects, and this is already a research topic in itself. However, by building a global frame of reference of the environment the ego vehicle is navigating, which can be accomplished through localization techniques, then all detections of static objects would be easily associated. Our method begins by determining an appropriate object detection network and an already labeled dataset to pre-train on. The data being used to pre-train should be as similar to the target data as possible to provide the best results. If a comparative dataset doesn't exist, then an alternative can be to use a synthetic dataset. Synthetic datasets can be organized to match the target data and provide infinite training data with minimal manual effort. To highlight this option, our experiments used the pre-sil synthetic dataset to pre-train our network and the KITTI dataset to test, as the pre-sil network was designed to imitate the data format of KITTI. We use AVOD FPN as our 3D object detection network, as it has been shown to produce well on both datasets. The following is a demonstration of a drive sequence in the KITTI dataset displayed through the colorized 3D LiDAR point cloud. The red bounding boxes represent detections made by the network having pre-trained only on the pre-sil dataset. In order to associate the detections, we localize the ego vehicle within its surroundings using the OrbSlam2 algorithm. This generates a global frame of reference. Shown is a 3D representation of a portion of the prior drive sequence, generated by transforming LiDAR scans to the global frame. As shown, the detections are also localized in the global frame. As the system propagates through the detections, those with centroids within a threshold distance to others are associated with a common ID. When all detections have been assigned an ID, the system progresses into the object classification and averaging phase. In this phase, an ID is classified as a static object if there are a minimum number of corresponding predictions, and a bounding box is determined for the object by averaging the dimensions, orientation, and centroid position of the corresponding predictions. Next is a secondary association and averaging procedure, as some predictions of the same object may not have been captured by the centroid association. In this step, averaged objects with differing IDs that overlap by a large enough margin are reassociated to the same ID and averaged again to produce a final label for that object. The final step is to propagate this label to all scenes in which the 3D bounding box label encloses a minimum number of points from the scene's point cloud, indicating that the object should be detectable in that scene. Of the nearly 29,000 KITTI labels of the car class, 68% were found to be associated with a static vehicle. By comparing our results with the initial predictions, we found that our process produced a 7% raise in precision and a 20% raise in recall, capturing 3/4 of all static car labels, including even the most difficult. In summary, we present a procedure that leverages a pre-trained detection network to predict multiple detections of objects over the course of a drive sequence, and uses the relative locality of these detections in order to generate preliminary labels for static objects throughout the dataset at no human annotation cost.